Good morning. This is Friday, February 5th, 2021 for Physics CP. I thought it'd be fun to create a series of problems to solve, calculator exercises based on the laws of physics and stuff that we've been studying lately. All right, so the first problem that occurred to me to create is to have a block that is moving to the right, and it's going to encounter a spring. Oh man, I was just thinking how more complicated I can make this. But I will terminate it here and say the spring is attached to a wall. And so now let's make up a few numbers. So I'm going to already pause this recording while students give me some numbers. All right, so thanks to help from my students, we've invented a physics problem to solve. And the physics problem goes like this. I have a block of mass 5 kilograms, and everything here is to 3 sig figs. I have a mass of 5 kilograms. This block is on a horizontal surface. It's initially moving at 4.30 meters per second to the right. And at this point, it encounters friction over a distance of 1.30 meters. The coefficient of kinetic friction is 0.340. So there's this rough patch, 1.30 meters in length, where there's friction with a value of 0.340 coefficient of friction. Right after the rough patch ends, if the block makes it past the rough patch, we don't even know that yet. If the block slides beyond the end of the rough patch, then it becomes frictionless, but now there's a spring attached to an unmovable wall. The spring becomes compressed a distance of 0.320 meters. And the question becomes, so what is the value of the spring constant, lowercase k, in this problem? Okay, this is a fine physics problem to solve. Your approach should be to look at this in terms of energy all the time. There's kinetic energy, there's internal energy or thermal energy, there's spring elastic energy. Maybe I should remind you of the equations that we would use. So kinetic energy is given by the formula 1/2 times mass times velocity squared. Gravitational potential energy is mass times gravity times height. Spring potential energy is 1/2 times k, the spring constant, times delta x squared. I'll write it this way: the distance that the spring is compressed or stretched. Internal energy is the negative of the work done by friction in trying to stop things from moving. And the work done by friction is the force of friction, which is always opposite the direction of motion. So I'm just going to write it with a minus sign. The force of friction times the distance that it slides. And for distance, I could write d for distance. I could write x for distance. Here, I use delta x, so I'll write delta x over here as well. Now, don't get confused because I have two different delta x's in this problem. The first one, so I'll call it 1, is the rough patch. And the second one is where the spring is being compressed. All right, so the students correctly figured out that the first step in determining what the spring constant is here at the end of the problem is to calculate how much kinetic energy we are starting off with at the beginning of the problem. And the students and I agree that value is 46.2 joules. Okay, so we're starting off with 46.2 joules at the beginning of this problem when I have a 5 kilogram block moving at 4.3 meters per second on a horizontal surface. Now what? Okay, so a student has suggested, well, now that we know the initial energy at the beginning of this problem, we can go to work and calculate how much the spring is compressed using the spring potential energy formula. However, another student has pointed out that we're going to lose some energy because there's friction in this section. And so really, the very next step we should do is calculate how much friction we're encountering over this patch here that's 1.3 meters in extent, where the mass is 5 kilograms, the surface is horizontal, the coefficient of kinetic friction is 0.340. Calculate, please, what is the value of the force of friction in this situation? Okay, so one of the formulas of physics that would be useful right now is the fun equation, the one that says the force of friction is the product of the coefficient of friction times the normal force. I think of that as being fun because sometimes we write the normal force as just lowercase n. If it's static friction, then we use the coefficient of static friction. If it's kinetic friction, then we use the coefficient of kinetic friction. All right, a student posed the question, how do we find the normal force? And the answer from another student was, well, look at a free body diagram. For that 5 kilogram mass that's sliding along, there's the force of gravity, which is its weight, which is mass times acceleration due to gravity. And since the surface is horizontal, the sum of all the forces in the vertical direction have to add up to 0. So the magnitude of the normal force of the ground pushing up on this mass is equal in magnitude to the weight of the block being pulled down to the center of the earth by the force of gravity. So we can calculate the normal force by setting it equal to m times g. By the way, this is only going to be true on a horizontal surface in the absence of any other vertical forces. So if I had a string pulling at an angle, that's going to change the normal force. If I were going down an incline, that would change the value of the normal force as well. I don't know if I went over this with you, but on an incline, the normal force would be mg cosine theta, and we're not in that situation, so don't worry about that right now. Okay, so my students came up with 16.7 newtons, and I don't quite agree with that because I want to emphasize that the direction of the force of friction is opposite the direction that the block is sliding. And so I'm going to slap a minus sign in front of my value from my calculator. So I'm saying the force of friction is 16.7 newtons in magnitude to the left in direction. Okay, so now the question becomes, now what? We've calculated how much energy we have in this block at the beginning of the problem. We've just calculated how much friction we're going to be encountering over this stretch here that is 1.30 meters in distance. Now what? Okay, so I asked my students, what now? And their learned response was, oh, we should calculate the internal energy, which is the negative of the work done by friction in trying to stop this block from sliding. Now, if that internal energy calculates to be equal to or greater than the initial kinetic energy, that means the block will stop before it even reaches the end of this stretch here, this distance of 1.30 meters. If it's exactly equal, that means it would stop at exactly the end of it. If the internal energy was a greater number than what we start off with, we don't end up with negative energy. It would just slow down, stop before it even made it off this region here. And then they went on and said, all right, well, after you calculate the internal energy, assuming that it is less than the energy we started with, you should subtract this from our initial kinetic energy, and that will tell us how much kinetic energy we have. I'll put a F for final. And final here means after we come out of this friction section. All right, that's a great plan. Go ahead and calculate, please, both quantities. First, what is the internal energy? How much work is done by the force of friction trying to stop this block from sliding? If that number is less than our initial kinetic energy, then take the difference, please, and calculate how much kinetic energy we still have after friction has tried to stop things. Calculate, please. Okay, so what my students have calculated is that the internal energy is 21.7 joules. And one student was wondering, well, should that be a positive number or a negative number? So let me try to clarify. Friction always opposes the actual or attempted motion. Friction is always in a direction opposite to the actual or attempted motion. So if I have a block and I'm pushing it up an incline, friction is pointing down the incline. If I have a block and it's sliding down the incline, friction is pointing up the incline. And if the block is just sitting there at rest on the incline, well, gravity is still trying to make it slide down. So it's attempting to slide down. So it's friction pointing up the incline that stops it from its attempt to move down. So friction is always opposite the actual or attempted direction of motion. And by the dot product, which is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between those two directions, since friction is always opposite, well, that means it's always 180 degrees. And the cosine of 180 degrees is -1. So the work done by friction is always going to be a negative number. We're defining the internal energy as the negative of a negative number. So I'm recording the internal energy as being 21.7 joules, and that's telling us the bottom of this box and the surface that it scraped against, they both became hotter in the amount of 27.1 joules. All right, so we got to enjoy our 3-minute break for a moment. If the block started off with 46.2 joules of kinetic energy, And then after that, went through a rough patch where friction stole 21.7 joules from this initial amount, then all we have left after we get through with this rough patch is 24.5 joules of kinetic energy. So it slows down. And yes, we could calculate what its new speed is, but really the problem that we were trying to solve was, what is the spring constant in this particular situation? So the block started off 5 kilogram mass that doesn't change, initially going at 4.30 meters per second. That worked out to mean it had 46.2 joules of kinetic energy at the beginning of this problem. As it went over a rough patch where there was friction, it slowed down. Friction stole 21.7 joules of energy from this moving block. It didn't steal all of the kinetic energy. So what we have left over is still 24.5 joules, meaning the block is still moving, but now it's moving slower than originally. What we want to calculate is what is the value of the spring constant, knowing that this block runs into the spring and compresses it until the block has stopped moving. The spring is compressed a distance of 0.320 meters. So the question becomes, how do we figure out, finally, the spring constant? Or what do we do next? All right, so my students tell me that we're now ready to find the value of K. This is the next step. We're going to talk about us. Us, of course, meaning the potential energy stored in a spring, which is given by the equation 1/2 times K, the spring constant, times delta x squared, where delta x is the distance that the spring is stretched or compressed. In this problem, the spring is compressed a distance of 0.320 meters. Calculate, please, what is the value of the spring constant? All right, so my students have calculated the spring constant is 479, and they weren't quite sure what the units are for the spring constant. So a reminder, it's in units of newtons per meter, newtons divided by meters. So at long last, this ends the first physics problem that we started today. And the problem was, I have this 5 kilogram block. It starts at 4.30 meters per second. There's no friction until it gets to a patch that is 1.30 meters long, where the coefficient of kinetic friction had a value of 0.340. After it came out of that rough patch, it then compressed a spring a distance of 0.320 meters. And we've just successfully calculated that the spring constant had a value of 479 newtons per meter. Ta-da! That ends problem 1. Okay, problem 2. I have a pendulum. Something that can swing from side to side. I have a pendulum, and it can swing from side to side. It makes an angle of theta with the vertical. All right, I'm going to establish some numbers here with my students. So here's problem number 2. I have a pendulum. It's a little bob that can swing back and forth, back and forth. And it has a mass of 0.220 kilograms. Again, everything to 3 sig figs. It's attached to a string that has a length of 2 meters, 2.00 meters. And although this angle looks larger than what's written, the random number is, this is 18 degrees that it makes with the vertical. And my question is going to be, when I let go of this, assuming that it's starting from rest, of course, so I guess I'll make that official. I'm going to release it from rest. And my question is, so how fast will it be moving at the bottom of this swing? Okay, the interesting physics problem. How fast will this pendulum bob be moving just as it gets to the bottom of this swing? Well, sadly, only one student seems to agree with me on what to do in this situation. And what the student suggested is that we use trigonometry. So I'm going to draw a horizontal line from where this plumb bob started, or this bob started, to where it is directly underneath this vertical line when this swing is at the bottom of its swing. This creates a right triangle. And in this right triangle, I know the hypotenuse, and I know one of the angles. Well, two of the angles, if you want to count knowing the 90-degree angle, right? So really, I can figure out all three angles. What I can calculate using trigonometry is the length of this leg of the right triangle. The total length from top to bottom of this swing is 2 meters, L. If I calculate the length of this side of the right triangle, then subtract that from the 2 meters height, that will give me this little teeny tiny value of h, which is the change in gravitational potential energy height for this bob. All right, that's what we're going to do. My student suggests that because this is the adjacent side relative to this 18-degree angle, that we use the cosine function from SOHCAHTOA. We say, okay, I want the adjacent side. I know the hypotenuse. I know the angle. The cosine of 18 degrees is equal to the adjacent side divided by the hypotenuse of 2 meters. Rearrange this equation and solve for the value of the adjacent side. All right, so what my students have worked out, not unanimously, but they believe that the adjacent length is 1.90 meters in length. If that's true, then the difference between 2 meters and 1.9 meters will be the length of this little segment here, h, the height of that bob above the bottom of the swing. So I'm going to just do that subtraction. 2 meters minus 1.90 meters means it's 10 centimeters. It's 0.10 meters is the value of h, the height of the bob above the bottom of the swing. 10 centimeters. And no, I can't take that out to the nearest millimeter because these were only known to 3 sig figs. I'm doing subtraction, so I only know it to the nearest 1 centimeters. All right, so armed with that, I believe you students have already figured out that I should now calculate. You might want to mute yourself. Calculate the gravitational potential energy that this object has. It has a mass of 0.220 kilograms. And when it's at an angle of 18 degrees above the vertical, from the vertical, on a 2 meters long string, that means its height is 10 centimeters or 0.10 meters above the lowest point. Calculate, please, what is the gravitational potential energy in this situation? Okay, so it wasn't quite unanimous, but my students got a value of 0.2. And I'm going to have to agree with them at this point because the height is only known to 2 sig figs now. The potential energy is going to have to be rounded to 2 sig figs as well. And so this 0 being just a placeholder, most students that I asked calculated 0.22 joules of gravitational potential energy. I agree. The question is, how fast is it moving at the bottom of the swing? So my next question is, now what? Okay, after a little bit of thought and discussion, my students are suggesting that this gravitational potential energy that we just calculated at the bottom of the swing is converted entirely into kinetic energy. And therefore, we can use the formula for kinetic energy, rearrange that, and finally solve for the speed of this bob at the bottom of the swing. That's the plan. Calculate, please. Okay, so by completely random coincidence, the 0.22 joules is the same number as 0.22 kilograms. So the kinetic energy divided by the mass cancel, and we're taking the square root of 2 as the speed at the bottom of the swing, and in decimal form, that is 1.4 meters per second. That is the answer to this problem. Now, just to tell you how much physics is fun, what I was originally hoping to do as my final problem today was have another pendulum, different mass, different length string, different angle, and at the bottom of the swing, have it hit and do a perfectly elastic collision with a block of mass m that would then go down an incline and then on a rough surface with friction to finally compress a spring at the end of the problem. That would have been a fun physics problem for sure. Unfortunately, the period is ended, and this concludes this video recording.